Hello, hello, it is time for lecture 19. Or if your video is flipped, it's time for lecture 19. Yes, 19, a prime lecture, a lecture of great excellence. Why? Well, remember, as of lecture 18, you are learning about light and light waves, electromagnetic radiation, and the geometric optics that lead from that physics to our vision, right? Why my glasses work, why contact lenses work, why telescopes and microscopes work, that geometric optic stuff and waves, and how we see, how our eyes use that concept of light waves as being both particles like beams, like hence geometric optics, right? And waves that carry energy. That's amazing stuff. It's wonderful. It's happy. Sight, right? Our human vision is based on that understanding of electromagnetic waves and electromagnetic radiation. Very cool. We have another kind of sensory system that requires waves, but this is a different kind of wave. And this is the kind of wave that we're going to talk about today. That's why this lecture is so cool, because not only are we talking about like the phenomenon of physical things, this kind of waves that are out there in the universe, and understanding them helps you understand like how energy moves around and stuff like that. But it's also, we're talking about why you can hear me. Why can you hear me right now, right? Isn't that cool? Can't wait to tell you all about it. All right, here we go. Now, let us remind ourselves previously, in a previous lecture, not too long ago, I asked you to read chapter 16.9 in the OpenStax textbook about waves, right? And what I asked you to do was to say, hey, will you do me a favor, read this thing about waves and learn about waves in a way that we didn't talk about in class, but it supplements it, right? And so this is what we're talking about. And if you saw that, if you were watching that and saw that the waves were showing how the material doesn't move, right? A wave is a disturbance. It's not the material moving from one place to another that carries the energy. It's the disturbance in the medium that carries the energy, right? Now we saw that for light, we have an even cooler thing in the sense that not only does the light get carried, right, because of or as a result of the wave, the disturbance, right, of the electromagnetic wave, but beyond that, the wave of light is also, right, has energy being carried by photons. Now, in this case, we're not going to be doing photons so much, but it's a different thing. But it's more like this kind of wave where it goes through media, right? But that wave doesn't look like this either. Notice what this kind of wave is. Like light waves, this is called a transverse wave. In other words, the up and down motion, right, of the medium, in this case, the surface of the ocean or whatever it is, with that fish in there, right? The disturbance goes perpendicular to the travel. So see, the wave is traveling this way, right? The wave is going this way. And you remember the speed of the wave, right? The v of the wave equals f lambda, the wavelength multiplied by the frequency, or more accurately, frequency by the wavelength, because f is frequency and lambda is wavelength, right? So the material is going left and right, or up and down in this case, while the wave is going from left to right. But there's another kind of wave, and that's a wave that allows us to hear. Okay, and that's longitudinal waves in this section we've talked about before. This is when you're pulsing stuff. You got dense, then not dense, then not dense, right? We call that compactification, rarefaction, compactification, rarefaction, right? Compaction or rarefaction. Compactification is a different thing about smashing dimensions together in string theory, but that's a different conversation. In any case, you have a situation where like the waves are going out, right? You get pulses. Now that's kind of cool. How does that work, right? Well, it turns out it works the same way. Even though it's a wave, it's still a disturbance, and you still have stuff moving, but in this material here, right, they go back and forth, kind of forward, then backward, then forward, then backward. You got compaction, rarefaction, compaction, rarefaction. And as a result, that disturbance also sends energy out. right? But it sends it through the medium, and you have to have a medium to compact or rarefy in order to make that happen. All right. And then you can do a combination of the two, like a guitar string. When I pluck a guitar string, it goes sideways. There's a transverse wave, like that, right? But when it does that transverse reaction, what happens is, right, as it goes like this, it pushes air up and down, right? Out, out, out. It pushes the wave like that, boom, and goes. And so it pushes the air. If it vibrates a few hundred times a second, right, then what will happen is that it will boom, 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 and it will create this wave of compression and rarefaction 400 times a second through the air. And it just doesn't go off in the one direction, right? Remember, waves, once they get out beyond that string, they go in every direction, right? So they go up and out, 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 out. So you wind up with this vibration, this wave that goes outward because the string is vibrating, right? That's how guitars work. That's how violins work too. And there's lots of really neat ways. And I'll tell you about brass and woodwind instruments a little bit later, maybe in this lecture, maybe the next lecture. But the bottom line is that is really powerful, cool stuff, right? And so you may remember back when you were a kid, when you were in school, and maybe once a year or so, you'd go visit the school nurse and put on some headphones. They would test your hearing, right? You would hear like quiet sounds or loud sounds. You would hear pitches, right, that were high pitched and low pitched. And then people would decide whether or not your hearing was okay. That's kind of important. Some of you may wind up becoming instructors and teachers of little kids even, right? And they're gonna have ear tests. Maybe you're going to be involved in audiology, right? And helping people figure out whether they can hear or not, because that might translate into speech impediments and so forth, right? People who can't hear very well have a hard time enunciating and speaking properly. So these are all these different things that you have to learn because it is extremely useful in whatever field you plan to go into in the future. All right. And by knowing how this works, you gain power and you gain understanding, and you can be amazed by how well our ears work. Remember when we were talking about the light energy reaching our eyes through geometric optics and through just light bulbs and electromagnetic waves like coming from the sun, for example, or from maybe a light bulb right over there? We were talking about that, right? And what we were realizing was the amount of energy hitting our eyes was tiny, right? Each photon of visible light is a few times 10 to the minus 19 joules. So even if thousands and thousands or even millions of photons were hitting our eye every second from a light source, that's still less than a billionth of a watt of energy that's hitting our eyes, maybe even a trillionth of a watt of energy hitting our eyes. So it's not a lot of energy, right? Compared to like something like a bottle of water, which I've been using for a long time. I just had to grab because you take a little bit of it, so I have my able to speak a little bit. Now, this right now, right, and as you know, I often have it at 1/5 fullness, but right now it's about 4/5 full. So that's because I refilled it recently because I was drinking water. And so if I take this thing, remember, if I take this and because it's 4/5 full instead of 1/5 full, I blew it 1/4 of a meter up, so like 8 or 10 inches. If I were to drop that on my hand, right, boom, that's 1 joule of energy that just hit my hand, 1 joule of kinetic energy. Now we're talking about billionths or even trillionths of a joule hitting my eye from a light or from the sun or from the sky, right? That is an amazingly small amount of energy. That's why I don't feel it. That's why it doesn't hurt me. But it does a lot of cool stuff in my system, right? And that's what you were doing all in the previous lecture in the study guide, talking about geometric optics, right? Index of refraction and stuff like that, equations, this, that, and the other. As you know, you didn't have to do a lot of math about it. You just had to understand it, know how it works, right? You might do some more stuff in the lab class about that, in the lab sections. Now we're going to do this about sound and the sound waves that hit us. And you'll find too that the amount of energy is remarkably small. And yet our brains, our eyes, we're able to make those things work. It's amazing. It's wonderful. All right, let's go on to it a little more. Get back to the textbook, which I think is pretty good about this part of waves. All right, so use the textbook as appropriate. You can know this, all right? We're going to section 16.10 about superposition and interference, right? And that's thinking about what happens when you have a light beam or a wave, right, interacting with other waves. Like if I drop one pebble into a pond, it's just a single boom, 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 boom wave going out from the center. But if I drop a handful of pebbles, then I got a lot of little going in different directions and everything is all like chaotic as a result, right? Well, it turns out you can figure out how chaotic or unchaotic that is. So I want you to take a look at this and read this. I'm not going to read it to you, right? I'm going to talk about the highlights as usual, but you should spend time reading it and understand how it works. And what you happen is produce this thing called constructive interference and destructive interference. The waves that come on top of one another, if like the crest of a wave hits a trough of a wave, they destroy each other and you wind up with nothing. But if a trough and a trough hit each other, or a crest and a crest hit each other, you can increase the strength of the wave, right? In this case, this is constructive interference. In this case, this is destructive interference. And then sometimes they don't have the same period, right? Their wavelength is different, or their frequency is different. In that case, you have an even more complicated situation where they're out of phase, it's called, and you wind up with lots of weird patterns that can come about, just like what's on the surface of the pond when you drop your pebbles, right? So this kind of thing. Take one big wave, for example, and one little wave with lots and lots, a high frequency, a short wavelength, and you wind up with a sort of combination. It's complicated. It can get kind of messy, but at the same time, it all makes sense. You're adding them together, okay, because the waves are traveling. But now think about this thing called standing waves. What if a wave just stays in place all the time? In other words, what if the wave's end is fixed, right? I'll give you an example. I'll hold this here, right? Here's my handy dandy spring here. What if I do this? I'm holding this end over here. I'm going to hold this end still. I'm going to wobble this side. What's happening to the wave in this case, right? The wave doesn't really do much. It stays in place and you wind up with this kind of thing. That's like a guitar string, right? Because the two ends are held together. And when you wave, it kind of does this, boing, like that. If I did it really fast, then I can get like two waves in there and they're standing. And so you've got points that are holding still and points that are moving fast. It's hard to see in the video, obviously. And also since this happens to be just a little plastic slinky that was obtained probably by one of my kids in one of their children's birthday parties many years ago. And now I'm just playing with it as a toy, but also using it to demonstrate deep physics. Yeah, kind of cool, right? Physics is toys. I mean, this is all physics. This is too much fun. You should love physics. I love physics. It's really fun, right? Remember, physics, some people are like, physics, but no, you are wiser than that. You know that physics is not that way, right? It's just another cool thing. But what it is, it's extra cool because you understand now how you see. Now you can understand how you hear, how you touch, how warm you get, how cold you get, how to lift somebody or a cat or whatever so you don't hurt yourself. It's all physics. It's beautiful. I love that stuff. Anyway, we're going to keep going. All right. So standing waves is a kind of way that you can get something to vibrate at a regular or at a predictable kind of way, right? Something that will bounce off edges and therefore kind of behave the same way at all times. And standing waves you can make happen just by swinging things at just the right rate, right? You create these things called nodes where they come together, these things called antinodes where the waves are far apart, and then the loop, which is the pieces there. And then you can get something called a fundamental. And then from there, you get what are called harmonics, overtones. This is a first overtone. Notice that here you have one loop, right? You have two loops, then you have the first overtone of this one loop. Then you have the second overtone if you have three loops, right? Third overtone if you have four loops, and so on and so on and so on. And you can even have beats, right? Where you have one that looks kind of the same, but the other one which is a little bit off, right? The speed might be the same, but the frequency might be just a little bit off, right? And so what happens is you wind up with some destructive and some constructive interference. You get a wah, 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 wah kind of effect, right? Jet aircraft, for example, will do that too. The combined sound sometimes gets louder and sometimes gets softer. And depending on what direction it goes, it gets really complicated. So it's kind of cool. All right. Where have you heard these terms before? fundamentals, overtones, beats. Now, I know Beats is the name of a particular company or a product, but what it is, you have heard these terms in music. That's right. When we are listening to music, this is what we hear. We are hearing lots of different tones put together, right? So, for example, if I'm just doing one wave of this kind of longitudinal acoustic wave, we call them, right? Because that's what sound is, right? It's causing this vibration. One, 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 one goes through out into space. The reason you hear me right now is because there's parts of my throat that are vibrating. And they vibrated just the right way that it comes out of my mouth when I pass air through them, right? And you wind up hearing this sound. Now, I will say that because we're doing this electronically, it gets even more complicated because it's worth 30 seconds of shall we say, distraction to talk about exactly what happens in this case, because it has to do with electromagnetic radiation too, right? I mentioned this a little bit in some previous lectures, but basically what happens is that when I talk and the sound comes out of my mouth, it goes through the air that I have, and it comes out and hits the microphone of my computer. Now, the microphone is basically kind of like my eardrum. It vibrates and it picks up the sound in all of its different levels, and then it codes the sound, it encodes it into electrical impulses. And then it does something called multiplex. It combines it using that, remember, constructive interference and the adding and the superposition and so forth, into another electromagnetic wave, right? Into like a light wave, essentially. But the light wave is complicated now. It's an electrical wave. It's a light wave, but it's got lots of pieces into it because it's like not smooth anymore, right? Because the code of my voice was put into it, right? Into this wave. And then electronically, this goes out through whatever wires, or maybe wirelessly, depending on how you're watching me right now. It goes out as a wave, right? That electromagnetic wave, the electromagnetic spectrum and stuff like that. Yes, that's what it does. And then it reaches a receiver of some kind, okay, possibly in your phone, possibly in your laptop if you're using wireless, or possibly even the set-top box or whatever that you're using that you're receiving this information from. And that electromagnetic wave gets decoded. Remember, it was encoded by my microphone in my computer and then broadcast out. And now your computer or your device, whatever you're watching on, decodes it and then brings it back. And so the electrical signal never, the carrier wave, right? It never, you have to hear that. You don't have to hear that. That's at the, megahertz and the kilohertz ranges that we're talking about. But the amount of sound that you hear comes back out of your, I guess it's a speaker, right? In your phone or in your computer, and you hear those sounds reproduced just as I said them, at least depending on how well the microphone recorded it and how well your speaker reproduces it. You hear some version of my voice, right? That's cool. Wave upon wave upon wave, superposition. It's the best stuff. You don't have to do any math on that, okay? You'd have to understand it though. You have to know how that works. There will be some concepts and ideas that you need to know how that all works. My voice right now, right, is a superposition of many, many, many sound waves. If it were not, it would sound very pure tone. Human whistling, by the way, is pretty close to pure tone. So if I whistle something like an A above middle C or something like that, roughly, right? You hear a very pure tone. Your computer screen, by the way, my recording might actually filter out that tone as noise. So you might not hear me very well. So I'll try it again. You may just hear a tiny bit of it. Depends on how your software and my software works. But I'll just blow a tone like that, right? And then maybe I have another tone, and then another tone, right? And then another tone, or some other tone lower. And you add all those things up in different amounts and different pitches and timbres and tones and loudnesses, and bingo, you have a voice, right? Or in the case of a standing wave of a violin, I scrape the bow across the violin that have some friction in it because rosin, right? And it will vibrate at a very high tone. Or I take a guitar string and I pluck it, boom, and that will vibrate the air. Same kind of thing. That's all vibrations. That's the sound that we hear. That's the physics of hearing and acoustic waves. That's music to my ears. I love that stuff. It's really, really cool. Okay, so let me share screen again so that you can get back to this concept of the mathematical aspect of it, right? Piano tuners routinely use beats in their work. That's when you have beats that are kind of sounding off. You want them to get closer, right? Like the faster they beat, the closer they are more likely to be the same tone, right? The frequency of a beat is the frequency of one minus the frequency of the other, right? It's basically the average of the two. And so you want, right? You want to get those as close as possible. And once you get them exactly the same, you don't have any beat anymore. Isn't that nice? Yes. So that's kind of thing. If you ever hear somebody do stuff, it says here, while beats may be annoying in audible sounds, beats actually have a lot of applications. It's really cool. For example, if you're doing ultrasounds, you can't hear ultrasound because your ears aren't sensitive to those frequencies. But you can use beats to figure out, oh, that part is a little bit thicker or denser, and it doesn't let light through or doesn't let the sound waves through as easily as that part. And as a result, that part can look darker in a picture or a video screen. And bingo, you have stuff that's lighter colored, stuff that's darker colored. You have a picture, you have ultrasound. Radar speed traps. Oh, yeah, we'll talk about that in a little bit too. What happens is you have a difference in the frequency between the radar beam that comes out of the police officer's radar beam thing, right? The speed measurer, and the speed, the wavelength, the frequency of the light coming back. All right, because your car, when it's moving, it shows a different wavelength. And when using that Doppler difference, all right, you actually are going to be able to find out some really cool stuff about how fast you're going. Let's hope that how fast you're going is not too fast. Anyway, so this is kind of fun, and I want you to look at it and read it. You might wind up using like one of these equations or something, but probably not. I just want you to understand it and know it and see how these things work, okay? And you're going to watch a bunch of other kinds of things, videos and so forth about waves and sound and acoustics and things like that, which is super fun. All right, and the last thing we're going to talk about right now is how you measure how loud something is. The amount of energy, remember what we were talking about? Yeah. In the next lecture, we'll talk about the physics of hearing a little bit, this chapter 17 stuff over here. But right now, we got to go to energy and waves, the intensity of waves. All right. Now, let me come back to you for just a second. Remember, we were talking about intensity, right? How intense is a wave? Right? Light coming at us, we can measure in terms of how much energy is hitting our eyes per second. But remember, our eyes have an area to them, right? So it's not just the amount of energy that, say, hits into my pupil. It also matters how big my pupil is open, right? So if, like, for example, I'm squinting, or if my eyes have adjusted to the brightness and the pupils have shrunk, or if it's nighttime and my pupils have dilated, right? That will be a total amount of energy will come in will depend on the area as well, right? So we've used this term before, but I'll use it again. In physics, we have this thing called intensity, all right? Intensity of a wave. A wave's intensity is how much energy is coming in, right? Is the energy per unit area. Now, sometimes this term intensity, especially when it comes to light, is also known as flux. All right. So it depends on what you've seen before. So if you looked, for example, on a light bulb package, sometimes on the light bulb package, it says the flux that this thing produces is in certain units, a certain number of what they call lumens. Okay. Which is kind of interesting. And so lumens is a flux thing. Intensity is another way to say flux, basically. And flux is another way to say intensity. It depends on what you're using it for. So you might see them interchangeable, but I just wanted to let you know that that's aware. And the units of intensity, right? Watts, that's energy per unit area, right? Over a certain amount of time. Watts per square meter. Energy per unit area per time. I should write that down. I shouldn't just assume. Sorry if I skipped a step on that one. Intensity and flux are the same as the energy per unit area per unit time, per amount of time. In this case, the amount of energy, a joule per second, right? That's power, right? And that's a joule per second, known as a watt. And so the meter squared is an area. So you can also call intensity or flux is the same as power per unit area. And how much power you get, because energy per unit time, okay, the amount of energy you get per amount of time is power. And then the amount of unit area, add that in there underneath, you divide that, you get watts per meter squared. Okay, so keep that in mind. When we talk about the intensity of wave, it's how much energy per unit time hits you per unit area, power per unit area. And I don't want you to get too confused yet. I know that you've heard of electric power in the past. We're going to be talking about that in a lecture or two. Excuse me. That's a little bit different from this, because not all electric power turns into the power of a wave that's coming towards you. It's a different kind of thing, but electric power does produce power too, and it's got its own kind of thing. And we will talk about that in some detail. But for now, okay, let's leave it at this concept of energy in a wave, all right, and the amount of power that comes out in a wave specifically, not in the electrical device, but in the wave, okay? So let's do that. That's in section 16.11, excuse me, 16.11 of the college physics textbook. So let's glance through it. Again, I'm not gonna read it through. I'm just gonna hit you the highlights, so you read it later, but I'll give you the outline and the shape of what you should understand and know when we're talking about the intensity of waves, right? Some energy waves can be directly observed, like earthquakes, which is kind of a bummer. Meanwhile, if you have like loud sounds, it'll really hurt your nerve cells in your ears, right? Ultrasound, can you deep change or take pictures? Laser beams, that's a very focused kind of wave of energy, right? You can do all kinds of stuff. So energy waves are very, very powerful. So here you go. Remember earlier we were talking about force, right? If you have a certain amount of wave, you're creating a displacement, right, that is resisted by a restoring force. So the amount of intensity, here is what we talked about here, the power per unit area, or the amount of energy per unit time per unit area. And so that is a really important unit of how intense a wave is. Now, for the sake of regular waves like what we hear, I was talking about those longitudinal waves, or they call them acoustic waves, right? You can figure out how much intensity there is. So here we go. Here's the intensity unit, watts per square meter we talked about, right? So light from the sun together, right? Infrared and visible and ultraviolet and all that together come out to about 1400 watts per square meter. If you just have infrared and visible light, it comes out to about 1300 watts per square meter, right? And meanwhile, when we're listening to sounds, we use the term decibel to figure out what that's called, right? The amount of power. 90 decibel sound level corresponds to an intensity of 1,000th of a watt per square meter. All right, they're going to talk about this more in chapter 17, but just so you know that this energy can be measured using interesting techniques. And I want you to learn decibels because it has to do with hearing, and hearing is cool. And I want you to hear, and I want you to know how to hear, okay? Know how things hear. So here's an example of calculating intensity and power. How much energy is an array of sunlight, right? Let's say the amount of sunlight coming from Earth's surface, something that you see, right, after it's gone through Earth's atmosphere and kind of scattered and gone through clouds and daylight, nighttime, etc., about 700 watts per square meter. So how much energy falls on that solar collector? How much intensity, what intensity would we have? And that's like use a magnifying glass. Remember, we're talking about magnification, right, in the geometric optics section that you just did not that long ago in the previous lecture, right? Then you can see just how intense you can make that magnifying glass focus that light. All right, and that's pretty sharp. If you want 5 million joules of energy, like hitting over 4 hours, right? And that's a lot. Remember, a million joules is, you can heat up some water on that. You can, a typical, remember how many joules per gram, how many calories per gram, calories and things like that, to raise the temperature of something 1 degree Celsius. Like a gram of water requires like 4 joules, 4.2 roughly, just about a calorie, like a small calorie with this little c, all that. And if you add all that up together, a million, that's a lot of cc's of water. So that's not an insignificant amount, right? Um, and so that's not bad. Then if you're going to go a little bit further and figure out just how intense you can get, whoa, this was already 5 times 10 to the 6 joules, right? But then you're going to try to do this and get that you can really focus considerably. And so in a smaller area, you can have much more power. You want to be a little bit careful, right? Have you ever written your name into a piece of wood with a magnifying glass on a sunny day? I've done it before. It's kind of fun. I don't know if I still have that piece of wood. I hope I do. It's kind of cute. I wrote my name in it in like a summer camp thing, or maybe it was like a workshop for school, one of those sleepover type things at a nature center. It was fun. And then one time I was foolish. I had a small magnifying glass. I accidentally turned it on my leg. Yes, by accident. I was like doing other stuff with it and like pointing on my leg, and I was like, ouch! Within like a fraction of a second, it got so hot that I had to move it off. I like fortunately did not burn myself because my body could sense the infrared radiation that had been focused onto one spot on my jeans. Thank goodness I felt that. Otherwise, could have been a bad scene. Burning, ouch, but that didn't happen. So I'm very happy with that. So the kind of thing that you want to go, I'm jumping back into 16.11. Okay, so you can see some of the things in combining the intensity of 2 waves. You can do that and create what was called constructive interference. So you wind up with a circumstance here, right? With rarefaction, compression, rarefactive compression. If they're both compressed at the same time, as we talked earlier about waves superposing, right? Then you get areas of loudness, right? Areas of greater intensity. And then you have areas that are destructive, where they kind of knock on each other, where the compression part and the rarefaction part cancel each other out, and they wind up being dead spots, right? So you say you're here, and you got these 2 speakers talking, right? You have constructive and destructive interference all throughout the room. So you might be standing here, it might be really loud, but you might be standing here, it might be really quiet. It's kind of weird how that works. You got to place speakers carefully so that all of those waves all sufficiently go around each other and add so that you don't wind up with any dead spots. When you're creating, say, a lecture hall or something like that, or you're talking, or you're in a concert hall, you have to make sure that all those waves are constructing properly and not creating dead zones and you don't hear very well. In fact, there are some famously bad examples of people who created these halls and they tried to make them look nice, right? So they're very pretty, but then when people started playing music in them, they're like, it sounds terrible. What's going on? Turned out that the destructive interference was so prevalent in the hall because of the way that the sound was bouncing around the edges and the ceiling and the floors and the seats and things like that sounded horrible. All right. I believe Carnegie Hall in New York City had to go through millions of dollars of refitting and retrospective fixing after it had been supposedly fixed once because it sounded so bad. I mean, it's really that kind of thing that happens. And you go to different halls, and some places are like, oh, Boston Symphony Hall sounds beautiful. Oh, Avery Fisher Hall in New York City, Lincoln Center, sounds terrible. It just depends on where you're going and how that did. It has everything to do with how these waves bounce back and forth, how they're absorbed, how they travel, and how they compress. All right. So that's the nature of those kinds of waves. All right. And how music sounds, those standing waves, I want you to keep those in mind. I'm just going to introduce the physics of hearing real quick, all right, in chapter 17. I would like to just get that started because you're already thinking about it. We're talking about these acoustic waves and how they do stuff, right? So I'm going to share screen real quick and just have you be ready to do this going forward for the next lecture. All right, the introduction to the physics of hearing. This is cute. This tree fell in the woods. Did anyone hear it? No one. If no one heard it, did it make a sound? Well, whether or not someone heard it, it totally made a sound. Why? Because the air is around it and because all those things happen. Whether or not we detected it, believe me, these little plants around here totally felt an acoustic wave, a longitudinal wave, stuff of compression and rarefaction, really thunking our ears. Okay. And so 17.1, sound is a longitudinal wave. We're going to talk about these things, right? Frequency, wavelength, pitch, difference, relationships between temperature on the speed of sound. Oh, that's kind of cool. Because, air is a gas, right? And depending on how those longitudinal waves travel through different media, they'll go at different speeds. And then we have the Doppler effect, sonic boom, standing waves. Well, we're going to talk about these, but not too deeply, because we want to get eventually to hearing, because this is the part that I want to talk about with you all most, because the way that we hear and the way that we talk about loudness and frequency and intensity and things like that, and acoustic impedance and ultrasound and Doppler shifted stuff and those radar guns that we were talking about before, that you can decide whether or not something is loud or quiet. I really want you to see those. Okay, I think this is a cool physics concept trailer. It's only a minute and a half. I want you to watch it. I think it would be fine and you'll learn something cool about it. But be ready, everybody, okay? Because what we're going to be doing, we're going to start talking about sound. And believe me, sound is cool. We now know how sound works, but now it's a matter of, can we explain it mathematically? Can we describe it in such a way, right? Rarefaction, compression. We're talking about this up to this point, right? The string moves to the left, it creates another impression, rarefaction, then to the right, then to the left, then to the right, and then it sends out this wave. Poof, that way, this way, that way, this way, that way, da, 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 da. Hey, and out it goes. And then in it comes, all that wave to hit our little tiny eardrum. Right? Remember we were talking about how small everything is? Right. You want to read this stuff, and I want you to sort of get a sense of it and just get started to understand that is how waves work. Wow. Right? That's neat. And so that's how sound works. So the last sentence here, I want you to keep in mind, right? The last two sentences, I guess. Whether the heat transfer from compression to rarefaction is significant depends on how far apart they are. It depends on wavelength. Wavelength, frequency, amplitude, and speed of propagation are all important for sound, just as they are for all waves. Okay? All right. So that's where we are going to stop for today. And we've got a few cool mathematical relationships that we've talked about already, right? And beyond that, we're now going to just go in next to the whole concept of how we hear and how the physics of waves, in this case, especially longitudinal waves through a medium, allows us to hear. It's the best stuff. Thank you so much. I hope you've been filling out your study guides. Remember to go and finish your study guides now. Okay. And if you have any questions, of course, ask me, ask your recitation instructor, ask your lab instructor. Thank you so much for your time. We'll see you in the next lecture. Okay. See ya.